Hey there, and welcome to This Explainer. Today we're diving into something called the double drop dilemma. It's this classic physics puzzle that directly pits our deepest, most human intuition against the actual literal laws of the universe. Specifically, we're going to be looking at the behavior of a feather compared to a solid iron ball. And I promise you, by the end of our time together today, you're going to see gravity and honestly the very air around you in a completely different light. So let's start by doing a quick little mental simulation. Picture this. Imagine you are standing right on the edge of the roof of a super tall building. In your right hand, you've got a solid, heavy iron ball. In your left hand, a really light, fluffy bird's feather. You hold both of them out over the edge, open your hands at the exact same time, and just let go. Picture that outcome in your head. What hits the ground first? Well, if you're like pretty much everyone else on the planet, your visceral instinct instantly tells you that the iron ball plummets straight down and smashes into the pavement way, way before that feather gently drifts its way to the floor. And honestly, based on everything we see in our everyday lives, you'd be absolutely right to think that. But there is an incredible intellectual friction here between our gut instinct and actual physics. Our natural intuition strongly screams at us that a heavier mass dictates a faster fall speed. Heavy things fall fast, light things fall slow. I mean, it just makes sense, right? Well, enter the legendary scientist Galileo Galilei. He looked at this exact problem and proposed a theory that completely shattered the conventional wisdom of his time. He argued that the iron ball reaching the ground first actually has absolutely nothing to do with its mass. No way. Instead, he claimed that the difference in the rate of falling is entirely due to how these objects interact with the air as they drop. In other words, it's air resistance that dictates the fall speed we observe, not the mass of the object itself. Which brings us to our first main topic: Galileo's challenge to intuition. Let's take a quick step back in time to explore the historical roots of this physics mystery and the man who first challenged our natural assumptions. Okay, so to truly grasp Galileo's argument, we first have to recognize the atmospheric drag that we are all moving through every single day. Air resistance is basically the invisible force from the atmosphere that interacts with and slows down falling objects. Think about it. When you drop that feather, it has a pretty wide surface area, but very little mass. So the air molecules push up against it, catching the air kind of like a tiny parachute and slowing its descent. The dense iron ball, on the other hand, just slices right through those exact same air molecules with way less pushback relative to its mass. So the difference in the falling speeds we observe here on Earth is entirely due to this invisible air pushing against the objects, not how much they actually weigh. According to a really famous historical anecdote, Galileo decided to take this wild theory out of his notebook and test it in the real world. To study gravity and the phenomenon of free fall, he reportedly carried objects of different masses all the way up the endless steps of the Leaning Tower of Pisa. Just imagine that scene for a second. We're in Renaissance Italy, and he's dropping differently weighted items from the very top of the tower, watching them plummet to the ground, specifically to prove to everyone watching that the heavy objects didn't significantly outpace the lighter ones of a similar shape. And from those observations, he arrived at a conclusion that was, frankly, just mind-bending for the era. Quote, "Objects fall at the same rate regardless of their mass." Galileo realized that if you could somehow magically remove the air from the equation entirely, like if you could drop that iron ball and that feather in a complete vacuum, they would fall at the exact same speed and hit the ground at the exact same microsecond. It's this beautifully elegant mathematical reality. But here's the catch. For centuries, it was incredibly hard to truly prove, mostly because it's pretty darn difficult to find a vacuum big enough to drop things in here on Earth. And that leads us right into the ultimate moon experiment. Because to definitively, undeniably prove Galileo's centuries-old theory right, humanity had to take the experiment out of this world. Literally. This right here brilliantly illustrates why space exploration is so incredibly valuable for fundamental science. Just look at the contrast. On Earth, our nice, thick atmosphere creates all that pesky air resistance that complicates our drop experiments. But the moon doesn't have an atmosphere. It is essentially a giant planetary-scale vacuum chamber. It is the absolute perfect, pristine laboratory for totally isolating the variable of air resistance. If Galileo was right, this was the ultimate place to prove it. So this incredible test actually happened right at the end of the Apollo 15 mission. We had astronauts literally walking around on the surface of the moon, and Commander David Scott decided to use this totally unprecedented opportunity to conduct a live physics experiment right in front of the television cameras that were broadcasting all the way back to Earth. He wanted to pay tribute to Galileo by recreating that famous drop, but this time doing it in a true pure vacuum. The setup for this was beautifully simple. Step 1, Commander Scott stands in front of the camera, and he's holding a heavy aluminum geological hammer in his right hand. In his left hand, he holds a remarkably light falcon feather. Step 2, he holds them out at exactly the same height and lets them go simultaneously, dropping them right into the stark lunar vacuum. Step 3, observe the impact. Just imagine the tension in that moment. Centuries of theoretical physics riding on this one incredibly cool visual demonstration. And the result? It was absolutely thrilling. As millions of people watched, the feather didn't drift, it didn't float or flutter. Without the atmosphere there to push back against it, that feather plummeted like a rock. The heavy geological hammer and the light falcon feather fell side by side, perfectly parallel, and they hit the dusty lunar surface at the exact same moment. It is such a stunning visual to watch. It was the ultimate vindication. Hundreds of years later, humanity stood on another world and proved once and for all that Galileo was absolutely correct. So, what should we take away from all this? Why does this actually matter beyond just being a really cool space trivia fact? Well, it's a powerful reminder to question what we think we know. For most of human history, people looked at falling objects and just assumed mass drove the speed, simply because they couldn't see the air doing the work. It really makes you wonder, doesn't it? If our own eyes and our deepest gut intuitions can completely deceive us about something as basic and fundamental as a falling object, what other invisible forces are shaping our everyday world? What other everyday phenomena are we totally misunderstanding right now, just because we can't see the hidden variables? Keep questioning, keep looking a little deeper, and I'll catch you in the next explainer.